Welcome back to our physics session. Today we're tackling a fascinating problem from astrophysics, calculating the gene's radius. This concept helps us understand how giant clouds of gas and dust in space decide whether to form stars or remain diffuse. First, imagine a large, spherical cloud of interstellar gas. Inside this cloud, there's a constant battle. Gravity is trying to pull everything inwards, while the gas pressure, caused by the motion of the gas particles, pushes outwards. Our diagram would show this spherical cloud with arrows pointing inwards for gravity and outwards for pressure. Now, let's identify our key players. We're given the mass of the cloud, m, which is 10 to the 30 kilograms, a truly immense mass. We need to find the gene's radius, rj. This is the critical radius where the cloud's own gravity overcomes its internal pressure, leading to collapse. We'll use some fundamental constants. The gravitational constant, g, Boltzmann's constant, kb, and the mass of a proton, mp. Since interstellar gas is mostly molecular hydrogen, we'll assume a mean molecular weight, mu, of 2.3. Crucially, for cold interstellar gas clouds, we typically assume a very low temperature, T, around 10 Kelvin. This is a common and necessary assumption in these types of problems when temperature isn't explicitly given. The gene's radius is derived from the balance between gravitational energy and thermal energy. A powerful equation for the gene's radius, Rj, given a cloud's mass, m, and temperature, T, is Rj equals g mu mp multiplied by 5 times kb t. This formula tells us that for a cloud of a specific mass and temperature, there's a particular radius. If the cloud is smaller than this radius, it will become unstable and collapse. If it's larger, it remains stable against collapse. Let's plug in our values. G equals 6.674 times 10 to the minus 11 Newton meter squared, kilograms cubed. Mu is 2.3. MP was 1.672 times 10 to the minus 27 kilograms. KB is 1.381 times 10 to the minus 23 joules, kk minus 1. Substituting these into our equation, Rj equals 6.674 times 10 to the minus 11 times 2.3 times 1.672 times 10 to the 30 over 5 times 1.381 times 10 to the minus 23. Calculating the numerator, 25.68 times 10 to the minus 8. Calculating the denominator, 69.05 times 10 to the 23. Dividing these gives us Rj is equivalent to 25.68 times 10 to the minus 8 minus negative 23, which simplifies to 0.3719 times 10 to the 15 meters. Rewriting this, we get approximately 3.72 times 10 to the 14 meters. Let's check if this answer makes sense. 3.72 times 10 to the 14 meters is a truly massive distance. To put it in perspective, 1 light year is about 9.46 times 10 to the 15 meters. So our gene's radius is approximately 0.039 light years. This value is well within the typical sizes of cold, dense molecular cloud cores that are on the verge of star formation. The magnitude seems perfectly reasonable for an astrophysical object like this. So, for a cloud of interstellar gas weighing 10 to the 30 kilograms and at a typical temperature of 10 K, its gene's radius is approximately 3.72 times 10 to the 14 meters. This means if such a cloud shrinks to this size or smaller, its own gravity will overwhelm the thermal pressure, causing it to collapse and potentially form new stars. This concept is fundamental to understanding stellar birth and galaxy evolution, highlighting the delicate balance between gravity and thermal pressure that governs cosmic structures. Remember, our calculation relies on assumed values for temperature and composition, which are typical for interstellar clouds but can vary in different cosmic environments. Understanding the gene's criterion is key to modern astrophysics. Thank you for joining this session. I hope you found this explanation of the gene's radius helpful. If you did, please like this video, subscribe to the channel for more physics content, and share it with your friends. Your engagement helps us create more resources. Feel free to leave any questions or comments below. I always enjoy reading them and helping you understand these concepts better. And if there's a specific problem you'd like me to solve in a future video, consider donating to the channel. Each month, we'll select a few donor-requested problems to tackle. See you next time.